So today we're doing area and perimeter of similar figures. It's the last lesson of the unit. So when we're done with this lesson, we're done with 2D figures, and we'll just have some practice days, a quiz, and your test is next Wednesday. So what we want to discover today is what happens when we take a figure and we dilate it. So let's say, tonight is Friday. At my house, it's pizza night. We order pizza. So what happens if I order one pizza, but then the next pizza, I half the diameter? I want it to be smaller. Not as many people eat the veggie pizza, mainly just I like the veggie pizza. So I want the diameter to be smaller. But what am I doing to the area of my pizza when I shrink the diameter? When I half the diameter, what did I do to the area? Did I half the area? That's what you don't have to answer. That's what we're discovering today. So what happens to the area and perimeter when we mess with the dimensions? So we're going to mess with the dimensions today, and we're going to see what effect it has on the perimeter and what effect it has on the area. So we're going to start off with a case study. We're just going to study two shapes, and we're going to see what we can find out about it. So this is kind of our experiment right here. We've got two squares. We messed with the dimensions. One of them has a side of 16. One of them has a side of 28. They're similar figures because they're squares. All squares are similar. So they are proportional. I want you to write down in your notes the ratio of the sides reduced, the ratio of the perimeters reduced, and then the ratio of the areas reduced. This is what we're studying, and then we're going to come up with some conclusions. So go ahead and write those in your notes right now. All right, so the ratio of the sides, good. 16 to 28 reduces to 4 to 7. Very good. The ratio of the perimeters, you find the perimeter of each square, which is really easy to find. 64 to 112, very good. And that reduces to what? It reduces to 4 to 7. The same thing as what the sides reduce to. All right, what's the ratio of the areas? Are you ready? So the areas are, you wrote it, good, 256 to 784. We don't care what the areas are. We're wondering what the ratio of the areas are. What did you get? There we go. Okay, 16 to 49. Very good. So what conclusion should we make here? What things are coming into y'all's minds?
And the ratio of the area is squared.
Do y'all see that? 16 isn't just a random number. 16 is 4 squared. 49 isn't just out of our back pockets. 49 is 7 squared. Okay, that was our first case study. We studied some squares. Now let's study some triangles. Let's make sure, sometimes things are a coincidence and sometimes things are a rule. We want to see if that was a coincidence or a rule. So do the same thing with these triangles. Find the ratio of the sides, the ratio of the perimeters, the ratio of the areas. Go. All right, so ratio of the sides, 18 to 6. Notice our units always cancel. 18 inches to 6 inches, the inches divided by inches is gone. Ratios never have units. So 3 to 1, very good. Their perimeters, you should have gotten 54 and 18. When you put that in your calculator and you math enter it, when you reduce it, you get 3 to 1. 54 to 18 is 3 to 1. And then Nathaniel had the hard part. He had to find the area of each one. The area of the first one is what? 81 root 3. And the area of the second one was 9 root 3. And the root 3's cancel, and 81 to 9 reduces to 9 to 1. You had it. That's perfect. Put the 1 back. Very good. So, did the same thing happen or not? Did the same thing happen?
Yeah.
So we had, the annotations are gone. Bye, thank you. On the last problem, we had the ratio of the sides matched the ratio of the perimeters, and then the ratio of the areas was squared. Did that happen here? The ratio of the sides matches the ratio of the perimeters, and then the ratio of the areas was squared. So I think if it happened twice, it's no longer a coincidence. It's a rule. It's actually how it works with similar figures. So here is today's lesson in a nutshell. Write it down. if two polygons polygons are similar. If they're similar, the ratio of the sides is A to B, the ratio of the perimeters is A to B, and the ratio of the areas is A squared to B squared. This only works for similar figures. So the ratio of the sides matches the ratio of the perimeters. It doesn't mean the perimeters are the same. It just means when you reduce the ratio, they're the same. Write these as with colons or with fractions. Either. Okay, ready to try some examples? So the way that we did the first two examples was inefficient. We didn't have to do it that way. That was too much work. Now that we know this happens every time, we are going to skip all the work. We're going to find 0 perimeters. We're going to find 0 areas, okay? That's the moral of this lesson. Shortcuts is the moral of the story here. Given the similar hexagons, find each ratio. This time we're given the areas. So the ratio of the areas is just 100 to 169. That does not reduce. We do not have to find the sides to find the ratio of the sides. We don't have to know the perimeter to find the ratio of the perimeter, because we know if the ratio of the areas is A squared to B squared, then the ratio of the next two things is A to B. How do we get A and B?
Square root.
Square root. Ratio of the sides, 10 to 13. Ratio of the perimeters, 10 to 13. You got it. How easy was that problem? It doesn't get much easier than that. Y'all can keep your annotations when you write them.
We can't keep that because when you move on, then it would stay there.
Yeah, but I'm just saying you can wait and erase it when I move on. Okay. Okay, so good, shortcut. Now that we know this, we can do this. Okay, next one. Given two similar rectangles, find the perimeter of the first rectangle. Okay, this one's a little bit different. This one we're going to be setting up a proportion instead of just a ratio. Now, if we hadn't learned what we learned today, that the sides and the perimeters have the same ratio, we would have to find the missing side. We'd have to go, okay, 115 minus 15 minus 15 divided by 2, find the missing side, use the scale factor, find the new perimeter. That was a lot of steps. Don't do it. No, don't. We're not doing that. Instead, what we're going to do is say 12 is to 15 as the perimeter of the first rectangle is to the perimeter of the second one. The reason we're allowed to say that is because sides are A to B and perimeters are A to B. Their ratios literally equal. So we are allowed to set them equal. So we put side is to side as perimeter is to perimeter. We cross multiply and the problem is over. We didn't have to find any missing sides. So just cross multiply. What do you get? You do it all in one step, guys. 12 times 115 divided by 15. What do you get?
92.
92 inches is the perimeter of the smaller rectangle. And no, we didn't find a missing side. We use the fact that the sides and the perimeters have equivalent, equal ratios. Let's try another one. Given two similar octagons, find the area of the larger octagon. Raise your hand if you love finding areas of octagons. No way, right? You have to do trig. You have to find the missing angle. It's a decimal. It is not fun. But if the polygons are similar, we get to use our shortcut. We get to use what we just learned. So what I'm going to do is say side is to side as area. Uh-oh, it stopped working. As area is to area. Do not cross multiply. Everyone stop what you're doing. Don't touch your calculator. This one's different because this one is sides and areas. Do those have the same proportion?
No.
No. Good. Remember, sides are one-dimensional, A to B, and area is two-dimensional, A squared to B squared. You can't cross multiply a 1D with a 2D. You can't do it. So what do you want to do about it? We have to make the dimensions match. Sorry, go.
Just square root of 15 over 9.
Love it. No, not times anything. No. To get something from 1D to where we want it, 2D, the only choice is to square it. Square it.
Just a second, I'll be right back.
Okay, so what I want you to do in your calculator is 15 squared times 45, enter, divided by 9 squared, enter. What is the area of the bigger polygon? I'm getting 125. Okay, erase that 225, please. The answer is 125 centimeters squared. You cross multiply these numbers right here. 15 squared times 45 divided by 9 squared. What questions do y'all have? Okay, I'm not hearing any questions. Let's try the next one. All right, here's what I was talking about with the pizzas. Yum, pizza. Lauren ordered 2 pizzas. The diameter of the small pizza was 1/3 the diameter of the larger pizza. Without annotating, guys, decide what you can conclude. Don't write anything yet. What can you conclude about the surface areas of the pizzas? So I'm telling you about their diameters, but I want to know about their areas. I'm telling you about their diameters, but I want to know what happened to the areas. Don't say anything quite yet. It's tempting to say, oh, the smaller pizza is 1/3 as big. The answer is A. That the amount of cheese you need is 3 times less in the smaller pizza, but that's not right, right? What are y'all getting? Everyone annotate and circle their answer. What's the right answer? There we go. I wanted lots of different colors. There we go. Yay! So diameters are one-dimensional. So when I cut the diameter of my pizza by 3, that's a one-dimensional change. Area, how much cheese you have to sprinkle on it, is 2-dimensional. So this is my A to B. I want it to be A squared to B squared because of this word right here. So the answer is 1/9. A squared to B squared. Okay, we love our annotations. A gardener plants tulips in rows in her 2-foot by 5-foot rectangular garden. If she plants 30 tulips in the garden, how many tulips would she plant in a 4-foot by 10-foot garden? Don't answer, just read and decide. Chisholm, what happened to the dimensions of her garden? What did she do to the dimensions of her garden?
She squared it.
5 squared is not 10.
Oh, times 2, I mean.
She doubled it. She doubled the dimensions of her garden. First it was 2-foot by 5-foot. I'm sorry, I'm saying her. Oh yeah, it is her. Okay, good. Now it's 4 feet by 10 feet. Her dimensions doubled. And it's so tempting to take the 30 and just double it. But what does 30 represent? We're planting tulips, guys. So is it an area or a perimeter?
Area.
Yeah. Look, she's filling it all in. The 30 is not one-dimensional. The 30 is two-dimensional because it's the area of the garden, not the edge of the garden. So I'm not going to do 30 times 2. I'm going to do 30 times 2 squared. Good. You need to make your scale factor from 1D to 2D. The only way to get from 1D to 2D is to square something. So it's 30 times 4. What's the answer? She has to go buy 120 tulips. That's actually really expensive. So by doubling the dimensions of her garden, she quadrupled the area. When you double the dimensions, you don't double the area. You quadruple the area. So there was a lot of effect on the area of her garden. This lesson was all nice and good, because it was a shortcut and it was very easy. And that's what the one page of your homework is, okay? But you know in life, we don't always change the shape proportionally. We don't always take the hexagon and double all the sides. It's not always similar. Plenty of times in life, you mess with the width, but you don't mess with the length, right? And so we want to know what happens when the change is non-proportional, when they are not similar figures. So similar, not similar figures. Okay. So if a rectangle's, oh, who typed this? Possessive. Okay. If a rectangle's original dimensions are 50 by 30, what change is made to the area within the length is shortened to 20? Here's the moral of the story. When the change is not proportional, there is no trick. There is no, oh, a to b becomes a squared to b squared. There's no shortcut. So when the change is non-proportional, you have to calculate the first, calculate the second, and see what happened. Kind of like when we were doing those case studies, okay? So the first rectangle is 50 by 30. What's the area of the first rectangle? 1,500. Good. My new rectangle, what are the dimensions of the new rectangle?
20 and 30.
Shortened to 20. Cool. Okay. New rectangle is 20 by 30. What's the area of the new rectangle?
600.
And then it just wants to know what change is made to the area. And that's kind of vague, right? You can write it as a proportion. Well, the area, 1,500 divided by 600, shrunk by 2.5, right? It's 2.5 times smaller. Smaller. 2.5 times smaller. Or sometimes it'll want you to subtract what's the difference in the areas. So if it wanted to know the difference versus like the change, you would just subtract them and you're like, oh, well the area is 900 less. So it's 2.5 times smaller, it's 900 less. There's no trick to this problem. You just solve both of them and compare the numbers. Let's try one more.